Today we will discuss a summary of the what our topic is, key topics we covered in modules 1 and 2. We'll just push off with this. We'll have a short review. Okay. Most of the things are familiar to you. Those who have attended the class, they would be familiar with these things. But those who missed the class due to some reason, this will be a first time they are coming across. So we were discussing about analytical chemistry first. So analytical chemistry basically involves identifying what substances are present within a sample, the elements or molecules. And there are qualitative methods which provides an idea about what all things are there, and quantitative methods which will provide the percentage, you can say, the amount of various substances, either the specific amount or relative amounts, that's there. So there are classical techniques as well as the instrumental methods, and in this subject analytical instrumentation we are dealing with instrumental methods for analyzing samples. Okay, so the classical method, your titration, all those things, gravimetric analysis, volumetric analysis, all those things are there. They are quantitative analysis techniques. Then there are other things, identifying qualitative analytic techniques like color, burning the thing, or boiling it, or mixing in some solvent. All those things are there. These are all classical techniques. Instrumental techniques, they make use of some physical property we are aware of. So far we have discussed all this absorbance spectroscopy. Absorbance of some portion of the spectrum by the sample. All those things, they rely on some optical properties of the material. So, and IR spectroscopy is there, where there is heat absorption. So different portion of the electromagnetic spectrum are being exploited. We have other techniques also which makes use of the charge to mass ratio, then NMR, nuclear magnetic resonance. Such techniques also exist. So there are variety of techniques which are used in the instrumental methods, right? So this is some of the characteristic properties and what is the techniques, instrumental techniques which make use of them. So we are dealing with say UV, visible, then electron, yes, fluorescence. Then for spectrophotometry we are dealing with this, so emission spectroscopy and absorption spectroscopy. Then Raman spectroscopy, we deal scattering of radiation. Then interferometry to some extent, RES. Then X-ray and diffraction, we discuss. Rotation we are not discussing. Polarimetry, all those. Charge to mass ratio, yes. Mass spectroscopy. Then radioactivity, no. Right. So such we will discuss all these techniques in your paper, okay, in this particular topic, right? So going to the next, there are data domains that we know we need to we have domains, data, the values, the quantities which we obtain, they will be in the non-electrical domain typically. It's maybe light, pressure, chemical, pH, all those things. They have to be converted into electrical domain. You may get analog signals from your instrument. For further processing, you may convert it into a digital signal. That's also possible. So electrical signals typically are analog in nature, whatever we obtain. This is the rough schematic of the block diagram of a typical analytical instrument. Source, there is a transducer, there's a signal conditioner, all this processing and display. So this is a typical setup wherever all instrumentation papers, they show these things. And there is a typical classification for different instruments, a photometer, atomic emission spectrometer, or colorimeter, that is charge, right? pH meter, all those things. It shows the various components. What is the stimulus? What is the information extracted, the domain, and then the readout. So transducer is also mentioned. The detector, detector, right? So we in this modules 1 and 2 we discuss all these topics, and yesterday we had a discussion about AAS, atomic absorption spectroscopy. We started off with fluorescence spectroscopy in module 3. Now we'll review these things. We'll review these 4 topics. IR we won't, photometry we'll review, right? So these are the texts. The best text you could find is this Skoog. Skoog is the best text. It has a very detailed discussion of lot of techniques. Some techniques which are very specific to our syllabus you will find only in Kandapur text. This one, textbook by Kandapur, and book of analytical instruments. It's a third edition is there. So it's not very updated book. That's one reason. Skoog is a very updated book, right? Spectroscopy. First we discuss about the electromagnetic spectrum, then the laws related to absorption of radiation. So that is, they should come here. Okay, they should come here, right? So all right. So spectroscopy. So that is interaction of sample with electromagnetic radiation. Most of them are electromagnetic, based on electromagnetic radiation. So we are aware what is an electromagnetic wave. There is the electric and magnetic fields, they vibrate mutually perpendicular to each other and also perpendicular to the direction of propagation. And being instrumentation engineers doesn't make you give you an excuse not to know an electromagnetic wave. There are you are aware of some things called as Maxwell's equation and all those things. Maybe some people might write gate papers in EC branch also. Okay, so you will, it's very well and good you start studying some things from the electromagnetic theory. All right, the basics are from your physics class. One thing point to stress here is that we explain a lot of properties of electromagnetic waves using considering the wave nature of the electromagnetic wave. Other things are explained using particle nature. It's a dual nature of electromagnetic radiation, right? And this is a spectrum. This is your visible spectrum, and 550 nanometers very good for us. That's what green, right? For good for eyes. That's what we are used some portion of the spectrum for analytical purposes, but not all portions could be used till now, right? We are not going into gamma rays or very long range radio waves for analytical purposes. Microwaves, yeah, up till to some extent we have used microwaves, right? So this is a visible spectrum, right? So there are some properties we discuss in this particular experiment. The double slit experiment is very well known to you. There is a constructive and destructive difference. There are nodes and antinodes. They are formed, right? Max, minima. That is one thing which we need to be aware of. That is then there is the transmission, reflection, refraction. All those process scattering. So these properties find use in some equipments which rely on optical principles, right? So absorption of radiation means there will be transition from the ground state to the excited state within the atom, right? And we typically, for an atom, you consider discrete energy levels, whereas for molecule we have different atoms of different substances, elements, and they interact in very complicated manner. You end up with energy bands, right? Then we have been seeing this diagram time and again. This is an absorbance spectra for sodium. Absorbance spectra is 589 and 589.6 nanometers. So, and ground states transition, right? Ground state to 3p1 and 3p. Okay, so this So this transition is accompanied by a de-excitation after some time. We saw yesterday 10 seconds or something. The de-excitation will cause emission of the same wavelength. That's the resonance. That's what we call as resonance. Right. Then there is absorbance spectra. For molecules, it is much complicated interaction. So, and we studied that there is interaction of the electronic states, then atomic vibration and rotational states. So, so that is because of that you have a complex band structure and lower energy transitions. These are small sub energy levels, you can say vibrational energy states. That is due to low energy things, that is IR. Higher energy transitions are caused by much more higher energy, say UV vis, okay, ultraviolet and visible spectrum, okay. Right. So that is regarding the transition states. We had a detailed discussion about that. You could check up those slides or the scoop text. Okay. This is especially true with the case of fluorescence. We'll revisit this thing when we discuss fluorescence spectroscopy in module 3. Right. Then Beer-Lambert's law. There is a relation. The transmittance is proportional to the reference to the transmitted radiance. So that's what. And the inverse is your absorbance. It's expressed as a percentage also, you could. So that is and both are, so at 0% absorbance means transmittance is 100%. We saw this figure also, right? Again, the Beer-Lambert's law gives a relation. There is a proportionality constant in terms of absorptivity. Absorptivity is a proportionality constant, right? And it's directly proportional to the length of the sample and the concentration, right? Optical path length and the concentration. And the length of the sample is often fixed in your equipment. You have a cuvette which is of a fixed dimension, say 1 centimeter cuvette. So Beer-Lambert's law variation for different molar concentrations of a particular material, rhodamin B solution. So you say the absorbance is increasing for as your concentration increases. The absorbance wavelength almost remains the same, around 555, around that. So it deviates. It's a non-linear characteristics of Beer-Lambert's law at higher concentrations. Okay, so low concentrations only it's valid. Then we discuss about optical spectroscopy. We take up one by one. That's what. We first discuss absorption spectroscopy, then we went to emission, then in third module we will discuss fluorescence. So first we'll take about absorption spectroscopy, right. There is this slide also we came across. Okay, the wavelengths, how they are classifying different techniques. Alright, NMR is very much related to your MRI, alright, magnetic resonance imaging. We'll discuss that technique in, I think, probably in fourth module something, right? Fourth or fifth module. Different components of the spectroscopic equipment. These are the different components. You have a source, then some mechanism to select the wavelength, then you have the sample, the detector, and some readout. And emission spectroscopy, the sample itself is emitting something, right? And that is observed. We will see this arrangement when we discuss fluorescence spectroscopy. We will see the emission spectra and we identify the substance. There are characteristics for this emission spectrum depending upon the substance being observed. Not all substances provide an emission spectra or a fluorescence spectra. That is very specific substances only provide this type of spectra, right? Okay, so next we saw a very important component, that's wavelength selector. A typical wavelength selector, this particular component, we have two types of things. One is a monochromator, other one is a what do you say, the prism grating base arrangement, right? This is a Turner grating monochromator, where there is an entrance slit through which the source light is focused on a collimating arrangement, and it is then focused onto a reflected onto a grating. So you have different types of gratings, and the grating can be moved around. It can be moved around. The position angle can be adjusted, and by that mechanism you will be able to select one particular wavelength, right? So you will be able to scan over a wavelength, you could say it like that, right? Range. And we came across a parameter which is to indicate the what do you say, how is the bandwidth, how you have a narrow bandwidth, that is better. I've left it in the slides. I just showing the key slides here. So you could select either lambda 1 or lambda 2 depending upon how you orient this thing. So this is your monochromator, which allows you to scan over a range of wavelengths, right? So yeah, this is a typical thing which we get. You slice the pulse. A 7 nanometer pulse is sliced to 0.35 nanometer width, right? Effective bandwidth, that's what we discuss. Then there is a prism based arrangement which is similar to the grating based structure. It also allows you to select the monochromator. You'll be able to rotate the prism, or such mechanisms are there which are not shown in this figure, right? Change the prism position by bit, right? So this is a typical absorption spectroscopy component. A detector, it came in here accidentally, right? Detectors, we have this is a summary of the detectors which we typically use in ultraviolet or visible spectroscopy: photovoltaic cells, phototubes, then photomultiplier tubes, photoconductive transistors. That is LDR, right? LDR type. Then silicon photodiode, right? Then CCD. Such arrangements are there. Then ultraviolet spectral regions also. So the classification we have come across the near UV, far, middle UV, and far UV. So then extreme UV classification is also there. And just follow the slide. That's what. Then the sources are very specific. Your UV region, you will use a deuterium lamp, mercury arc lamp, all those things, xenon lamp. Visible region, the tungsten filament lamp, the sources, right? And photometry, colorimetry, that's a topic. Basically, photometer measures the intensity of light, and it is a simple instrument. And there are two types of photometers. The basic arrangement is like this: you have a source, and then usually in the visible spectrum, use a visible spectrum. You have the source, and this source is the source is measuring the light which is passing through a sample. First you will put the reference sample in this path, and then you will take a measurement I0, and then you will put the sample of interest in this pathway, and then you will take a measurement. The ratio is the absorbance. That is the key idea in single beam photometers. Double beam photometers, you will split up the light which comes from the source into two pathways. Here you are shown a flow cell through which the sample flows. So one of them will be reference channel, the other one is the sample of interest, and then you will measure the in two separate detectors, and then you will take the difference. It's a differential output, right? Then colorimeter basically it's a measurement color. So you can say it is another way to measure the transmittance or absorbance of light passing through a sample. So there are two types of colorimeters basically, say color densitometers and also color photometers, and it's based on Beer-Lambert's law, right? There is a Beer's law as well as a Lambert's law, right? So this is this we have come across. What is it? I'm not going to read it out, just follow it. We discussed quite in detail in the class, right? So, and you will be able to identify the substance. Both these apple shown here are red in color, but they are not, even our eye is able to perceive what is it. So there is some difference, and there are color spaces defined by standard bodies, and that is used as a reference to indicate which is red, which is this particular color. So it's like your paint shade card, which they give numbers. When you paint the house, you get a shade card. Same manner, they have references to indicate which is which color, right? So this is your colorimeter arrangement, and this is your colorimeter arrangement, right? And we can identify the various components here. It's basically a filter which filters the color of light of interest into this sample, and you make a measurement using a photodiode. Over here what is shown as a photo resistor. Then spectrophotometers, we saw the differences between a spectrometer and a spectrophotometer, like that. Again this thing comes again. So right, usually you will measure the intensity of light and versus the frequency, right? Frequency or wavelength, both, either of this. So colorimeter we saw. Then spectrophotometer is a combination of spectrometer and a photometer. That's what it measures: intensity, light intensity as a function of wavelength of light, right? Single beam, double beam in space, and all those things we saw. Yeah, it's the same thing, swapping the sample within this channel. That is what you will just first put the reference channel or reference cuvette, and then you will just take a measurement P0, then you will just put this sample in this channel and then take a reading. That's how the transducer, the typical one, photodiode, photomultiplier, photovoltaics, and all those things. Double beam space, you have a beam splitter arrangement which splits the beam that's come from the source, right? There are some optics here and also shutter to take a reference reading, right? Difference amplifier and use. Then there is a double beam in time where you have a mirror which is on a disk which has some portions grayed out and some portion as mirrors, and some portions which are transparent. So transparent portion, this is rotated by means of a motor. So the transparent portion transmits the light through of the disk will transmit the light to this channel, the sample channel, and the reflecting portions, the mirrored portions, will reflect the light onto this particular channel. So you will take two separate readings, and you have some mechanism which is called as grid mirror, which combines the output of these two, and you take a reading, right? Again, this is a spectrophotometer. It shows all these components, various components, right? Then IR spectroscopy. IR spectroscopy is basically you are going to measure the heat, and the sources also are different. Sources are there. Globar source, different sources are there. IR sources are radiation sources are required. Okay, so the classification of infrared spectral regions is also just like UV classification. There is a classification like this. So IR is occurring in the vibrational states and vibration lower energy states, and we saw the molecular vibrations that will absorb this energy, IR, and then energy in the IR band. So this are dipoles in a typical HCl molecule. So there is a fluctuation in this dipole moment, and if your incident IR radiation matches this vibrational frequency, then there is absorption, right? And that will change the amplitude of this molecular wave. After a time, there is a stability, but this is what you make a measurement. That is, you say that some IR frequencies have been absorbed. That's what you will detect it like that. Rotations can also change. Rotation of the molecules, they can also bring about fluctuation in the changes in the IR absorbed, right? This is a typical NDIR, non-destructive IR instrument. So different sources, Nernst, Globar, incandescent wire source, mercury arc lamp, all those are sources. They are gratings, then thermocouples, okay, thermal detectors, all those things are the typical arrangements. Then one particular thing which we discuss is the Fourier transform infrared spectroscopy, where you have an interferometer arrangement to convert this IR absorbance data into the frequency domain. So what you do here is that this is the Michelsen's interferometer arrangement we discussed in detail. Okay, you have a source, so it radiates, and there is an arrangement which is called as a beam splitter, right? Beam splitter, you call it as a beam splitter, right? And this splits into two halves. So one will travel towards this mobile mirror side, other half travels to this fixed mirror side, and again they are reflected back. Both of them are reflected back. So this is a pathway, one, then goes like this from this beam splitter, and again they will travel back to this beam splitter, and a portion is reflected back towards the source, other is transmitted to the sample, through the sample, right? And it is detected. So you are denoting the path length difference between these things, these two what do you say, fixed mirror and the mobile mirror. This mirror could be moved around, and you could take a scan. So at some positions corresponding to lambda, half lambda, you are again getting a path length match, and at positions like C and B, there is a path difference is maximum. It's almost like a cosine wave. It's almost like a cosine wave, the output. So the readout is obtained as in terms of a parameter which is called as a delta, difference in path length, delta, 2 into m minus f. This m is this mobile mirror path length, and f is this. It travels twice, no? The beam travels twice through this path. So, and you could move this mirror by some motor mechanisms, and this particular plot is called as an interferogram, whatever you get from the interferogram, from the detector, and you will take the Fourier transform of this interferogram. One-sided spectra is taken. It's symmetric, that's why. And that shows you gives you the frequency components present. Now we discussed that the Fourier transform itself has a limitation. It doesn't give you time localization. It will just show you what all things are present. So that's a thing which is more of interest in your signal processing side. If you need a time localization, we are here in this analytical instrumentation. We are only bothered about what is present, what frequencies are present, right? And these are signatures corresponding to a particular substance. We have data sets to which we can, not data sets, we have references to which we can compare. That's how you identify known substances. New substances, you will obviously do other studies to corroborate your results. That's what. So for existing substances identification purposes, you will compare with known databases. So that is